Discovery's 4 computers now have primary control of critical vehicle functions.
All right, everyone, welcome to today's ASRG webinar. But before we get started, I'd like to tell you a little bit about ASRG and get some of the legal stuff out of the way. ASRG is a nonprofit organization founded to support the development of the automotive security industry. We have developed a platform and a community to share knowledge, communicate through networks, and to build value with collaboration. This is a community for you, built by you, with the goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get more involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Before we jump into the presentation today, let's get some of the legal stuff taken care of. The views and opinions expressed in this webinar are the views of those that have made them. They do not represent views or opinions of ASRG and are to be considered as informational. The use of this information is to be used by the individual and/or organization at their own risk.
Hi everyone, my name is Tianqi. I'm glad to be here and share my presentation with you all. I'm especially grateful to the Automotive Security Research Group for inviting me to speak. Today I will be a talk about Athena, Advanced Threat Knowledge Base for Networked Automotive. Athena is a powerful knowledge base that automotive industry can use to enhance the lifecycle interaction with the V model. In this presentation, I will explain why we need Athena and how it can help us improve our security measure. I will also share a case study to illustrate its effectiveness. Let me introduce myself. I'm Tianqi, and I'm the research team lead at SiteCraft. I'm focused on the topic about automotive security, cloud security, and AI. And I'm also a certificate automotive cybersecurity professional by SGS. I present many research at various conferences, including Black Hat Europe Arsenal, Usenix Poster, HitCon, and CyberSec. SiteCraft is an AI company based in Taiwan. We use autonomous system and human AI collaboration to automatic SOC operations, forensic detection and response for clients like the Fortune Global 500 and national government. We also offer managed detect and response, incident response, threat hunting, and accurate remediation. So we have a lot of different kinds of experience and skills. First, as an AI company, we are experts in AI and large language models. In fact, we are present at Black Hat USA 2023, the top cybersecurity conference, on how to use the large language model to interpret command line execution in the endpoint. This innovation helps reduce the workload of the human incident analyst and speed up the investigation progress. Second, we have a lot of real-world experience fighting with APT groups because of our location. This experience has given us a deep understanding of adversarial thinking and their action. We even published an investigation targeting Taiwan's semiconductor in Black Hat USA 2020. Last, we know the power of the graph, so we have incorporated graph theory into various scenarios, including incident investigation, constructs, cyber threat intelligence correlation to the graph. And we also published the research on how to perform AD attack path analysis using graph in Trooper conference. This kind of experience and skills is crucial for the automotive industry today. AI and large language model can help us reduce human effort in various tasks, such as in Tara, where AI can help map threat scenario and analyze impact rating using historical data. and more. Our experience in APT investigation teaches us how adversaries gain initial access to a network and how they move laterally and impacting the system. This technique and tactic might also target vehicles as network become more complex and closer to TCP/IP-based network infrastructure. Then attack path analysis and knowledge graph experience can help us analyze attack path during TARA. In our upcoming talk, we can see how to transfer this experience into the automotive field and build a resilient cybersecurity environment for the industry. Then here is the agenda for today's talk. First, we will talking about automotive industry in the background section. We will discuss the regulation 155 being enforced in Europe and the related standard ISO SAE 21434. In the second section, we will explore the challenge and the difficulties might meet when implement ISO SAE 21434. We will look at a consulting case study to help us understand this challenge better. In the third section, I will introduce you the Athena, Advanced Threat Knowledge Base for Networked Automotive. Then we will talk about and how to integrate Athena with ISO SAE 21434 in the next section. After that, we will have a case study about how to implement. Then finally, we will wrap up the conclusion that summarizes what we have covered today. In the background section, we will dive into the current state of the automotive industry, with a special focus on the regulation environment in Europe and the urgent need for the related standards. Here's the timeline showing how cybersecurity rules for cars have changed over time. The United Nations Economic Commission for Europe starting enforce rule for car cybersecurity in January 2021. This rule has become must for all new vehicle types by July 2022 and will apply to all new vehicles by July 2024. Looking at this timeline, it is clear that this rule has already need to be enforced. The quick pace of this rule shows that the car maker and everyone else involved need to make sure they are following them and are ready to protect their vehicle from cyber threat. Regulation 155 placed a big emphasis on building a cyber management system called CSMS. This system is crucial for automaker and supplier to manage cybersecurity risks through the vehicle design, develop, and operational process. However, the regulation itself doesn't provide specific guidelines on how to implement this system. To address this, the standard ISO SAE 21434 comes into play. It offers instructions on how to implement the CSMS in a way that aligns with the regulation of 155. Now, let's focus on the life cycle of ISO SAE 21434, which using a V-model approach, a popular framework in the system developed. This V-model is split into two parts, the left side and the right side. On the left side, we start with the concept and design phase. This is where we brainstorming high-level ideas and gradually get more specific about how we will implement them. Once we have done that, we move to the right side. On the right side, we start by checking that the low-level implementation detail match the design phase. Then we move to the validation phase, where we can make sure that the initial concept meets our goals. Each of these phases is important, but the concept phase is especially important. Without a thorough analysis during this phase, it is hard to design a good implementation and plan a good verification validation program. As the saying goes, a good start is half the battle. To do security by design right, we need to do the concept phase well. And the main focus of the concept phase is threat analysis and risk assessment, or TERA for short. The idea behind TERA is to encourage vehicle manufacturers to think about what kind of cybersecurity threat would make their vehicle unsafe and how to deal with them before they happen. This proactive approach helps prevent accidents instead of just fix them after they happen. Then let me give you a quick rundown of what TERA actually do. Take a look at the diagram on the right. It shows the whole TERA process. On the left side, you will see the example of the formula for TERA calculate the risk value. The first step in TERA is to identify assets, thinking about what is valuable for adversaries, like autonomous systems. We also need to think about what will happen if assets get compromised. Next, we come to the fork in the road. One is for the impact of the risk and the other is for the feasibility for the risk. For the left, we will be an impact rating process to determine how severe the risk is. This will involve considering all possible damage scenarios. On the right, we look at the feasibility of this risk. This involves thinking about threat scenario and mapping out a path an attacker might take. This helps us figure out how likely is that someone will carry out such an attack. Once we have figured out the impact rating and feasibility rate, we can calculate a risk value for the system. It is important to remember that both of these rating processes are based on what the analysts think. Different analysts must come up with different results. After getting the risk value, analysts can ranking the risk based on this value and decide what to do about each one. And that is the quick overview of TERA. So now we have a basic idea of the background, and let's talking about the challenge that come up with when we trying to put the standard ISO to SAE 21434 into practice. In this section, we will show a consulting case study that will help us understand the challenge we face during TERA implementation. This is the architecture for our consulting case study. The main network is the CAN bus, which is a robust, effective communication system commonly used in vehicle industry automation and other embedded systems to enable multiple microcontrollers and devices to communicate with each other without needing a central computer. To keep different scenario systems to be separated, there are a central gateway to manage the network between different subnets. Within the human interface subnet, also known as the CAN HMI, there is infotainment system, commonly referred as the head unit. It features a multimedia player and wireless connectivity for both driver and passengers. Move on. The diagnostic subnet called CAN-D play a crucial role in the local and remote diagnostic. It can access most of the ECU across different subnets. For remote diagnostic, this CAN bus utilizes a T-box with 4G, 5G capability, serve as a central hub for telematics data collection and communication in vehicle. Lastly, we have the CAN-B network, which is responsible for body control system, like the body control ECU, and this is the most critical subnet in these three subnets. Before they engage us our consulting service, the manufacturer has taken on the task for perform Terra independently and was
referred to implementation phase. Here is the snapshot of their initial plan. Following the Terra analysis, they point out the body control ECU as a critical component, one that they could cause significant problems
if compromised. Their top priority was to protect the body control ECU. To achieve this, they decided to implement the ECU protection solution. Then, in the verification phase, they intended to seeking the help for a third party to conduct a system penetration testing. On the surface, this plan appeared reasonable, but upon closer examination, we discover some stranger things, and let's break down step by step. During the Terra phase, they identified body control ECU need to be protected. But they didn't mention that the weakness of the body control ECU is spoofing attack, because it is hard to verify the sender on the canvas, making it easy for attacker to force functional signal to the body control ECU. Despite this, in the implementation phase, the ECU protection solution they choose can effectively address spoofing attack. It could only detect abnormal execution flow at the binary level. To counteract spoofing attack, they actually need network level access control or anomaly detection. If this mistake has been identified during the verification phase, they could have implemented temporary remediation. However, there is a potential blind spot as for the verification phase with the third-party penetration testing team. The testing team might attempt to intrusion from device connect to the internet, such as T-box and head unit. The limitation for the ECU protection solution might not be fully discovered during this testing. This discovery underscores the importance of the thorough and holistic cybersecurity planning. While the individual mistake may have seemed like an isolated incident, further analysis has shown that this is a part of a large pattern. As we dive deeper into analyze the entire process, we found the whole picture of the problem. First, we analyzed the challenge within each phase for the process. Here is what we have discovered. In the concept and design phase, the major challenge emerged. The first challenge is the lack of the global view. Without the global view of attack technique, it is hard to enumerate complete threat scenario, and will highly depend on the knowledge the Terra analysts have. Moreover, the new attack technique and concept will be explored and updated within the day. It will spend a lot of time for Terra analysts to follow them. So this is the first challenge. The second challenge is a known root cause of the threat. Without the fully understanding of the root cause and the methodology behind mitigation and detection solution, planning effective solution for specific scenario becomes a difficult task. As we move into the implementation phase, we face the other challenge. Analysts can easily misunderstand the coverage and effectiveness of the mitigation and detection solution when the marketplace is full of fancy buzzy words. It can cause them choosing a wrong solution that cannot mitigate the risks they identify. Then in the validation and verification phase, The primary issues come from black box or gray box penetration testing. This kind of testing is closer to real-world attack scenario, but it may lack of systematic verification plan. This shortage results from pen testers have only limited resource and knowledge about the system's architecture and internal information. Having analyzed the challenge within each phase, we now turn our attention into the interaction between these phases. We have observed that the challenge in the implementation phase can be partially attributed to shortcoming in the concept and design phase. It insists that the result of Terra may not effectively translate into practical mitigation and detection solution. Similar, the challenge in the verification and validation phase comes from the information from previous phase cannot effectively be leveraged. Therefore, we have identified a central issue: information inconsistencies. Each phase don't have the equal information. However, the V model is a continuous process, require a smoothly exchange of information between each phase to ensure effective. The information inconsistent may cause the blind spot in this model. To address the issue of inconsistency, I'd like to introduce the main character, the Athena, Advanced Threat Knowledge Base for Networked Automotive. This is Athena. You might notice that it is similar to MITRE ATT&CK. And you are right, our knowledge base is based on MITRE ATT&CK. Our goal is to make it fully compatible with MITRE ATT&CK, including providing detailed information about data source, software, threat actor groups, and mitigation strategy. However, our knowledge base has a distinct focus on attack scenario within automotive domain. And this is the attack technique page. And as you can see, it aligns with MITRE ATT&CK. It is designed to be intuitive and familiar, so there is no need to extend explanation here. After introducing the attack knowledge base for automotive, let's move on to introduce how to integrate the attack knowledge base within the ISO SAE 21434. First, in this figure is the V model process and common solution offered by automotive cybersecurity solution provider. In the concept and design phase, you will typically find Terra tool or consulting service, which help in identifying and assessing threat. Shifting our focus to how to integrate a technology base with Terra. As a follow-up to our previous analysis, lack of global view on attack technique and unknown the root cause of attack technique are the challenge in Terra. To overcome the challenge, the key factor is objectivity and availability. The main purpose of the objectivity is that analyzed results should be consistent from different analysts. To achieve this, we have broken down our approach into attack technique, which represent the smallest unit of attack method. We believe that every attack scenario can be effectively expressed through the combination of this attack technique. If by any chance an attack scenario can be fully expressed, our solution is straightforward. We just increase the required attack technique until the scenario is fully accounted for. This approach ensures that we have a comprehensive framework to handle any cybersecurity challenge, leaving no room for gaps or inconsistencies. And availability is the output result that not just free text information, but also need to include corresponding detection mitigation methodology. After identifying the risk, the next step is to convert this awareness into specific action. Each attack technique within our framework comes equipped with its own set of detection and mitigation methods, making it easier to implement effective mitigation. After achieving these two requirements, the output should encapsulate the best practice solution provided by our knowledge base and not ambiguous for implementation phase. Now, let's shift our focus forward into the integration process with the implementation phase. As a follow to our previous analysis, misunderstanding, mitigation, detection, coverage of solution is the challenge in implementation phase. To overcome the challenge, the key factor is quantification and classification. Quantification means quantify the detection and mitigation coverage of the solution that's selected. To illustrate this, take a look at the figure on the right. This is the quantified result of the CAN intrusion detection system. As you can see, the result demonstrates that attack technique related to network-based threat can be mitigated. The result of the quantification can help us understand the mitigation coverage for each solution to minimize the probability of misunderstanding. But it is important to note that while quantification is essential, not all of the solutions can be easily quantified. Alternatively, the classification can be considered. In this step, we use CDM, Cyber Defense Matrix, as a classification tool, which is a framework created by Sonia Yu to help expertly navigate the cybersecurity landscape. CDM allows us to rapidly classify assets and identify the protection stage that align with the selected solution. The figure on the right illustrates the pre-classified common solution. When we move to the verification phase, there were two inputs from previous phase. The result from Terra, which include component mapping to specific attack technique, and the result from the implementation phase include the mapping of selected solution to the corresponding mitigation attack technique. Now, let's move our attention toward the integration process with the validation and verification phase. We will explore how to use this result in this phase. The challenge in the verification phase is the lack of systematic and comprehensive verification phase. To address this challenge effectively, the key factor that comes to play is effective verification. Verification plays a crucial role. The most important mission in verification is to verify the effectiveness of the proposed solution, but not discover a new vulnerabilities. It is used to confirm the proposed solution is not only effective but also addressing the identified risk. By leveraging the result from the previous phase, we can plan a comprehensive verification process. The result from Terra can guide us verification based on the most significant threat scenario identified during Terra phase. Utilize these outcomes of the implementation phase. which enables us to check if the risk claimed to be mitigated by the selected solution is really done. This systematic approach ensures that we not only identify the most significant potential threat, but also validate the effectiveness of the solution. And this is an overview and recap of the phase along with their related key factor. So now, we can move into the case study. How we practical example to illustrate how to apply the attack knowledge base in a real-world scenario. Let's revisit the consulting case study that I mentioned at the beginning of the presentation. However, this time we will incorporate the Athena into the lifecycle. Now, let's follow the V-model lifecycle to demonstrate how can be seamless integrate with the attack knowledge base in real-world case. First, in the concept phase, the Athena will be integrated with Terra. The first step in this process is to identify the attack technique that are mostly likely to target each component based on its attribute and feature. We call this list the potential attack matrix. For example, let's look at the T-box component. It is involved in remote connection, remote diagnostic, remote control, and it is connected to the CAN bus or network. By analyzing this attribute and feature, we can figure out the attack technique that mostly like to target it. Repeat this process for each component, and you will have a complete list for potential risk matrix for the whole system. And in this table, we can see that the T-box has the attribute about remote access, which means that it has more initial access than IC and gateway. Following the identification of potential threats associated with each component, the next step is to analyze the attack path for each of these components. In the abstract layer of this analysis, we will systematically enumerate each attack path based on the attack technique associated with each component. As you can see in the animation, there is a path start from the T-box, pass through to the gateway, and reach the body control ECU. Another plan begin from the head unit and lead to the body control ECU. Additionally, there are load-sensitive paths that lead to the IC. The feasibility rate and impact rate can be explored by those information. Next, we can enrich the attack path by incorporating the potential attack matrix we analyzed in the initial step. This allows us to create an attack graph cover the entire system. And this is one of the outcomes of our attack path analysis. It is the same example we discussed earlier, which is an intrusion begin from the T-box, traverse the gateway, and automatically affect the body control ECU. Adversaries can exploit 4 distinct initial access methods. After lateral movement, it can lead to 5 different types of impact on the body control ECU. Each attack technique has predefined mitigation and detection strategy. So we can export the mitigation and detection strategy for the attack path. In this attack path, the adversarial heavily rely on lateral movement through the CAN bus network. Consequently, we will notice the network segmentation in the list of mitigation strategy. Moreover, considering that the initial access point for the attack path involves exploiting the T-box, we also find related mitigation mechanisms like Vehicle Security Operations Center, Exploit Protection, and App Sandbox. All of these potential mitigation and detection solutions can be considered in the following phase. When we complete the concept and design phase, we have a list of best practice mitigation and detection solutions. In the next step, we will select and apply this solution in design and implementation phase. Now let's dive into the implementation phase to understand how we can effectively leverage this information. In this case, we demonstrate how we using the cyber defense metric to conduct an evaluation. In the previous phase, each attack technique comes with its own set of mitigation, and there may be overlap between mitigation for different attack techniques. To simplify this, we gather all the mitigation across the entire system and mapping them into a CDN graph with counter as shown in the figure. In this graph, when a mitigation counter exceeds 30 times, it is marked in red. If the counter falls between 10 and 30 times, it is labeled purple, and so on. The visual representation helps us quickly identify the importance for each mitigation, and we can see that the network-based mitigation have the most overlap, such as the network segmentation CAN IDPS. It is because that the core network of this architecture is CAN bus network, which is not inherently designed for security. Consequently, we need to implement additional mitigation for this type of network. Moreover, the Vehicle Security Operations Center have also high overlap, because most of the behavior-based events can be monitored by it. This example shows us how to leverage CDM doing a quickly classification for the mitigation and figure out the gap of the whole system. After finished implementation, we will get into the final phase, the validation and verification phase. We will explore how we can effectively utilize the information gathered during the previous phase. In the validation and verification phase, penetration testing plays a critical role. It is in verifying the system's security. In the past, penetration testing has primarily seen as a means to discover vulnerability. However, rather than discovering vulnerability, validating whether the mitigation solution we have implemented are effective and functional is more important. To achieve this goal, we need to leverage the information from previous. The output from Terra, which include most significant risk, and the output for selected solution, which include the attack technique, can be mitigated. Those information serve as a valuable resource for red teaming planning their penetration testing program to verify that potential threat has indeed been addressed. In this case, the attack technique in the figure is related with T-box, and our red team leverage this information, select specific attack technique to construct an attack flow aimed at compromising the system and validate if the risk has been mitigated. Penetration plan initiate from the intrusion point by exploring the radio interface and deploy a backdoor in the boot script. It processes to harvest credentials within the system, leverage this credential for lateral movement. Ultimately, accessing the CAN bus network and successful accepting the information flow through it. This case exemplifies how we leverage the information from previous phase to craft a comprehensive penetration testing plan, ensuring the robustness of our cybersecurity measure. So now, let's get into the final part. In conclusion, the V-model outlined in ISO SAE 21434 is a structured, iterative framework. It manages cybersecurity throughout the automotive lifecycle. Each phase is connected by a continuous flow of information. However, many current cybersecurity solutions are implemented in isolation. This creates challenge in maintaining consistent, synchronized information across phases. Such fragmentation can reduce the effectiveness of cybersecurity measures. Insight gained in one phase may not seamlessly inform the next. The lack of flow can leave gaps in security and compliance. To overcome this challenge, a centralized knowledge base is essential. A shared repository can serve as a single source of truth. It enables smooth data exchange across teams and functions. This fosters a more integrated approach to cybersecurity management. One solution is Athena, a global accessible attack knowledge base. Athena is designed specifically for automotive sector. By centralizing cybersecurity knowledge, Athena bridges gaps in the V-model lifecycle. It enhances consistency and ensures that insights from one phase benefit others directly. This approach not only addresses information inconsistencies, it also fosters a more robust and resilient cybersecurity ecosystem. With Athena, automotive manufacturers, suppliers, and other stakeholders can align their cybersecurity strategy. They can respond to emerging threats more effectively. This collective approach advances the automotive industry toward a more secure future. Thanks for taking the time to listen. If you have any questions, feel free to reach out to me at the email address. Thanks.